You don't even know where that came from, bro.
Just
I had to tell him that his
1.58.
pen rose.
That's 1.58 dimensions right there. They just cracked some quantum code that has to do with this fractal.
I recently was listening to someone give a talk on yet another, like the 10,000th, new theory of physics, where this person was saying that he was working on a theory where inside every point of space, so starting off with like a normal length with height space coordinate system, and then inside every point of space was an entire like subspace universe of more points that was shaped like that triangle. So within every single regular point of space was a whole fractal triangle that existed inside it. And I don't know if I fully understood the motivation behind this, but it was very trippy, the graphics he was using to explore this idea.
Oh, for sure, dude. For sure. This fractal is gonna be end up being the key to it all right here.
I love the idea of the fractal dimension. So cool to think about. So this guy's idea was to imagine things like electrons, like we see them moving around in space, but what we don't see is that even when it looks like they're at a single place in space, they also have a position in the triangle, like in the fractal triangle, and they're like hopping around within it. And that's supposed to do something important. I'm not sure.
Electrons don't exist, bud.
Electrons don't exist?
Nope.
Oh, that's a
Electrons.
good one. That's a good start
Um.
to a topic.
Well, I mean, this has been the start of the topic for a long time.
What do you mean?
I mean, Tesla talked about it. J.J. Thomson, upon his discovery of the electron, prior to receiving the Nobel Peace Prize award, called it a corpuscle of dielectric capacitance that terminates on one ferritic tube.
Hmm?
Yeah, this preconceived notion of an electron on the conductor destroys the analogy between the dielectric and the magnetic. And you can't separate the dielectric from the magnetic within an electric field completely, right? Because electricity is not a thing of itself. Electricity is not the flow of electrons as they presumed it to be. It's just a complete farce. It's illogical and it's absurd. Tesla said it, Steinmetz said it, Heaviside said it, many others said it, and these are like the people that gave us our entire electrical understanding that we still use today. So, do you know what the spatial volume of an electron is, Easy?
There's no known listed spatial
Right,
volume.
right. So, do you know anything else in reality that simply has no quantifiability to it, but we still presume its existence?
Other than things like electrons? No.
Well, there is
They're
one other. There is one other. Highly suspicious. Um, neutrons, or not neutrons, sorry, neutrinos.
neutrinos, yeah.
Yep, yep.
Oh, and
Um,
quarks.
muons. I mean, there's a lot of other like things that break down from there, but fundamentally speaking, um, there's nothing else, dude. I mean, by their own standard of existence, right? It completely contradicts itself. So
I don't know what you mean by that. And I also, I both don't know when you say electrons don't exist, like what version of the electron you have in your mind that you're saying isn't true. It might very well be that I agree with you, that you're saying there's a specific theory of what the electron is and that's not real. So we'd have to dig into the details of this a little bit more. I definitely don't imagine electrons as being like hard little spheres or something. because that would immediately run into paradoxes regarding then the claim that there's no known size that they have.
Yeah, sorry, I was like in the middle of something, but yeah, I mean,
That's
like
okay.
based on the standard of existence from like the current mainstream model, is it has to be quantifiable in some regard, like on its own regard. Um, but they don't do that, right? They're looking at interactions of these fields, these dynamic fields, interlacing, and at the intersection of these two mutually antagonistic fields intersecting, they're presuming a particle, but it's literally just an intersection, is all it is. But again, like based on their standard of existence, if you can't quantify it, then it simply doesn't exist. And unfortunately, electrons aren't on their own are not quantifiable.
Do you know what a cloud chamber is?
Yeah, it's just a probability distribution.
No. No, I don't mean electron cloud. I mean it's a thing that you can build. Basically, you take a fish tank and you fill it with an alcohol vapor until the air inside is super saturated with alcohol. And then if you put something like anything that's slightly radioactive within it, you'll see these like streaks, like shooting off through the vapor. So people look at that and they say, like, oh, we're seeing particles, we're seeing things that are breaking off from the radioactive material and, going like, through the vapor. We see the streaks through the vapor. And you can do the same thing with electrons, like shoot electrons into this chamber, use magnets to make them spiral and dance around.
Sorry, dude, I had to take a bathroom break, which consists of a bottle and both hands.
Mm. Are you driving?
I just pulled over. Yeah, I'm on the road,
Makes
but
sense.
yeah, that's my bathroom.
Yeah.
But I mean, it's still a presumption, right? Like, I mean, just because you see like a phenomena, like, doesn't mean like you can necessarily say, oh, electrons is the causal mechanism here, like without ever having isolated one to support its existence. I mean, it's very presumptuous.
Well, we have isolated the things we call electrons because there are these like singular streaks that are seen within these chambers, and you can like make them spiral and move around in different ways using magnets.
Uh,
Um,
you can't trap you can't trap an electron. You can't isolate an electron. Same with the photon. Same with the virtual particle. Like these things are just kind of assumed more than anything. Um, but yeah,
so there's like these very delicate things they call electron guns. I forget exactly the engineering of them, but they're meant to fire electrons like down a barrel. And there are like chemical films that will light up at impact. And if you do this in a very dark room with one of these chemical films and then the electron gun, like you see like little individual strike dots that appear on the
well, that's how
film.
they created the CRT tube set television.
Yeah.
But I mean, to assume that it's electrons hitting something, I mean, again, it's just an assumption.
Well, I mean, is what you're seeing is something discrete. You're seeing a countable number of little dots of impact spots on the film. Like, oh, there's one, there's one, there's one. You know, as you watch the film, you know, suddenly like these little dots keep appearing on it.
Yeah, right. But again, I mean, that's to say that's an electron. I mean, it's very presumptuous.
Well, I think it's only presumptuous if you say something specific, theoretical about what the electron is. Because, like, all I'm saying here is that there's all these things you can do where electricity seems to come in these little chunks, each of which makes an individual little, you know, impact spot
Well,
on a film.
you gotta understand what electricity is, though,
As a
dude.
definitionally, an electron.
Right,
Yeah,
definitionally.
that's sort of the point. Is like I'm not saying I'm saying sort of I'm defining the electron by this by um yeah.
Experimentally, it could be asserted that, oh, that's due to actually some other thing or a combination of two things. But currently, the electron guns are designed such that what we call electrons are shot out of them one at a time, discrete,
Yeah.
smallest possible units, so far as we know.
And that's the point, is that there is a discreteness here, that like you turn down the power of the electron gun and you get these little ticks of the individual impacts of something against the film that they're firing at. Um, yeah. Same with the photon gun. So whatever the fundamental nature of electricity is, it seems to come in chunks.
Well, the fundamental nature of
And any changes
electricity.
been proposed different fundamental. Yeah.
Yeah, so when I hear the word electron, I just think of it as like the word we've given to like one observable chunk of electricity that we don't seem to have a way of further subdividing.
They subdivide it further into coulombs. They say that 1,000 coulombs equals one electron. Essentially, they perceive it as being like this clown car, right? Where you get 1,000 coulomb clowns that climbs into a single car, and as that car travels down the road, it stops on one phoretic line. The doors pop open, and 1,000 coulomb clowns hop out, equating to one electron. That's
Well, but that,
essentially.
I mean, that's just a unit choice. I don't even think in terms of coulombs. I just think
Well, we
of
don't.
like,
I mean, I'm
yeah.
not trying to define it based on its, bulk unit of quantification or however you want to deem that. I'm simply telling you that it's what the mainstream story is, and I don't agree with it.
Right. Well, the coulomb's definitely not the natural unit. So the way I think about it is just that, like, when people define the coulomb, they were only ever looking at large flows of electricity. And with much more delicate machines, when you turn down the power enough, you see that there is a natural unit of electricity, a kind of chunk unit that it seems to come in. And I would just say, okay, that's what, by definition, I'm calling the electron.
Well, I just pulled up the work here. But yeah, I mean, you got to understand what was said, early on, in the fact that electricity is comprised of two things, right? Inducing one another, and that's the dielectric and the magnetic field. And you can never separate the magnetic component from electricity due to the fact that electricity is not a thing of itself. I got to get back to work though.
Sure. Yeah. Good chat.
Mad food. Yeah, bro. Can't hang getting old. Getting old. It's good though.
Not much. I was asking what was the topic DZ was sending me about. They were talking about if the electron exists and something about um bad analogies by science entertainers.
Yeah.
Well, I mean, it's even worse when you look at the mainstream's answer to these things, right? And how illogical their assertions are. Completely illogical and ridiculous. They're atomist, right? Everything to them is a particle, right? Particle interactions. And unfortunately, that's just not how reality works. Not everything is based upon particle interaction rather than field dynamics. And they know nothing about fields. So to them, everything is just a bumping particle because they're materialist.
I'm fundamentally a fieldist in terms of my belief about what core reality is.
Well, okay. So then surely you've got a definement of a field.
Yeah, I mean they're very tricky to pin down exactly. I mean, at a literal level, um, a field is something that can measurably exert force and transmit energy across space, like the electric field is sort of the prime example. Like when I think of a field, I think of it as something that I could detect as like a exertion of force at a particular point in space.
Well, unfortunately, a force isn't a thing of itself. A force is what something does, not what something is. And furthermore, there is no particle, right, to support the existence of any field. So if a field isn't comprised of particles, then what is it?
I would not say that I think the fields are comprised of particles. And you're right, force is an action. It's what something is. So when I say, like, I have detected an electric field, that means I've detected some exertion of force. If the force being a transfer of energy and momentum. Um, so I've got some device. That device is sensitive to experiencing certain types of force, and when it picks up force in a particular place, I'm like, there's an electric field here because
I mean,
my detector is detecting something.
we're just choosing new words, right, without defining the terms. Like you're invoking energy, right, which science has never explained, be it potential or kinetic. They've never given a definement on energy. They've never given a definement on field. So it's like all these things are just kind of being taken for granted. Like, oh yeah, this is what's happening. But at the end of the day, what are we really saying? Because we're just kind of talking past one another when we invoke a field without defining what a field is in lieu of force and energy.
Sure. So I'll tell you how I think about it of constructing up from base observations to these bigger concepts. So like yeah, so we got to get energy and momentum locked down first. So I think about starting with like the billiard ball table, and I've got my ruler and my stopwatch, and I'm looking at the speed of these things as they collide with each other, and I'm trying to pay attention to what is the pattern here of like what determines how fast something's moving after a collision compared to right before the collision. And that's where I discover the concepts of momentum and energy. That momentum and energy, like, are what I come to when I'm looking for some quantity based on the motion of objects that is consistent before and after the collision. Like light object hits heavy object, the heavy object is not moving as fast after the collision as the light object was. Okay, but is there some other quantity here that is the same after the collision? And yeah, there is, mass times velocity. So I call that momentum. So there's a mechanical definition of energy and momentum as something that we see that's holding consistent before and after collisions with physical objects. Then we move on to things like magnets and stuff that we see pushing and pulling on each other in a way that's much harder to understand. So when I measure a particular amount of force, the force being a transfer of energy and momentum, and I already defined what that was from the billiard ball example. Like if I'm looking at, okay, I've got a magnetic billiard ball and another magnet pushes it a certain amount. That creates my definition for the magnetic field. The magnetic field is how strong at a given place in space is a magnetic billiard ball going to be pushed by another magnet. And that's what I'll call the magnetic field.
But I mean, that's literally just a description. Like you're literally talking about a specific amount of energy within a specific proximity, which
Yeah.
isn't really a definement of a field. That's more of just like a roadmap on how to perceive what's taking place through observation. But that's not an
Yeah, no,
explanation, and it's
that's what
definitely
I
not
like
a
about this.
logical, concise, rational explanation.
That's what I like about this is this definition of field is literally just the surface level observation. I don't know what the deeper meaning of it is. I'm
Do you
just
realize what an explanation is supposed to be consistent of?
I guess this isn't the type of explanation that a lot of people might want for the situation because it is just a descriptor of the observation.
Right, which isn't an explanation. I mean, descriptions are useful, sure, but when we're doing science, the epitome is to get to the explanation, be it a logical, concise, rational explanation, not just some faulty framework, which, we're kind of perceiving things through, but ultimately isn't the case. And that's kind of the mainstream's, sentiment at this point.
So, right. So I guess then what I would say is going forward from simply defining the field as like the surface level detection of force between things. Um, then
Well,
the
you
next
have to,
question.
you can't just invoke force without identifying a force of what, by what, and to what. And if you can't do that, then just simply throwing force out there, like, really isn't doing any justification.
No, I have a good definition of force. It's the transfer of momentum.
Okay, but we're just talking about motion now. Like, we're not really talking about what the force is consistent of.
Right. I'm mapping the patterns within motion, right? So I start just looking at billiard balls clinking into each other and identify that there's this quantity called momentum that seems important to pay attention to. And then I look at the case of magnets pushing on each other. And now that I already have a definition of momentum, I can say, like, this magnet gave this other magnet a certain amount of momentum when it pushed it away. And that amount of momentum that one magnet gives the other magnet is what I'll call the magnetic field. So yeah, I'm putting definitions to observations, and I'm mapping out, the landscape of how things move. And then the next thing I would look for is, okay, so what are the patterns of the magnetic field? Like, what are the interesting observable properties that it has? And try to map that out as well.
Well, it's a worthy attempt, but unfortunately, science doesn't even have an explanation behind magnetism either. They literally talk about very archaic terms like pushing and pulling, attraction and repulsion, and
Right, that's the observation.
it's
So,
yeah, but it's a very cursory observation. When you start
so,
really looking into magnetism and you realize that there is actually no magnetic attraction taking place, it's just
so,
a inacuity.
right. So how would I go further? So after I've looked at the basic idea of one magnet pushing on another magnet, the next thing I would do is put one magnet down on the table and just pour iron powder all around it. Give the table a little shake, and then the iron powder forms, distinctive streaks, right? So I'm looking at what the magnet does to all this iron powder around it. Again, surface level observation. But what the streaks make clear is that there's some interesting geometric patterns appearing. And now I can start really analyzing and cataloging, like, what are the
Well, that's
geometric
kind of what
shapes?
Faraday did when he came up with this
Yeah.
concept of the force lines. But unfortunately, there are no lines pertaining to magnetism, and there is no forces pertaining to magnetism other than the
We get the iron
central
powder streaks.
centrifugal divergence. Yeah, I see the streaks there. I understand that, but what you're not getting is that there literally is no line involved in magnetism. What you're looking at, right, are the field flux lines, but those aren't necessarily lines per se. Those are three-dimensional force vectors.
Sure. That's all I meant
Yeah,
by line. I meant the streaks, right?
I know, but it's a gross concept that Faraday came up with, which was inaccurate. I mean, it was accurate enough to describe what was taking place and to kind of move along further, um, but yeah, there are no lines, and certainly none of that which pertains to forces.
Well, look, there is no definition of what the magnetic field is that you will find in any physics textbook
It's
that
a problem,
does go deeper than simply saying the streaks that would be there if you blew iron powder around a magnet to see them,
but that's a
right?
problem. That's a problem when magnetism is the one intrinsic and extrinsic to all, component to all phenomena. It should be at the forefront of every scientist's investigation as to what is it, right? How do we accurately define what this thing is? But unfortunately, they haven't done that, and they haven't
We
done
have a
that with a
definition.
lot of things.
We have a
Go for it.
definition, a good one. You don't like the answer. The definition is the streaks that would be there if you poured iron powder around the magnet.
That's not a definition. That's a very vague description at
No,
best.
no, it's a super specific definition. It just lacks explanation to you. Like
Well,
you don't feel like
again,
it's a sufficient explanation, but it's a super specific definition.
I mean, what do you think the difference between a definition and an explanation is?
I think that there's a massive difference, right? Because like a definition just has to be like operational. Like it doesn't have to answer deeper questions that you have. Like let me put it this way. I've used this analogy before. Like what a thermometer reads is a good definition of what the temperature is. It's not an explanation, but it's an operational definition. Like it's a working thing that you can use. It's not going to tell you what temperature is, but it lets us all know how to define a number to put to it.
Yeah, again, like this is a materialist, right, agenda to try to quantize everything into existence, but that's not getting to a concise explanation, which is the epitome of science. Um,
I
if you're just
actually don't think that the purpose of science is to reach the type of explanations that I think you're looking for. I think it's just to create a kind of functional, working understanding of how to manipulate things. Like,
no,
if
no, no. That's current consensus based science, which isn't science at all. Those are just glorified mathematicians seeking to quantize everything into discrete chunks of particle interactions. That's not the original connotative science, right? And this is the
it may
problem.
not be,
Science
yeah.
is There's a huge separation in science, and when you define something, it should be based upon a logical, rational explanation. And sure, I understand like you're going to get deeper into things, and those deeper into things shouldn't necessarily have to be solely confined to the cursory definition. But when that definition isn't even touching on what the thing in contention is all about and just being left off with vague, ambiguous descriptions, we're never really getting to the essence of what this thing is that we're talking about. And I could give you an example with an elephant, right? You've got four blindfolded men standing around an elephant, all each touching different parts of the elephant and describing to an accuracy what it is that they're interacting with. One guy's got a hold of the leg and he's describing what seems to be like a telephone pole. And another guy's got a hold of the tail and it's kind of curly and lengthy and he's describing some sort of like rope type thing. Everybody's 100% accurate within their descriptions, right?
Mhm.
But until they stand back, take off the blindfold, and look at the subject, right, they've never gotten to an accurate definement through these vague, ambiguous descriptions, even though they were 100% correct. But there's a big difference between a rope, a tree trunk, and an elephant, right? So it's very crucial in science that we get to a concise, logical explanation, right, upon defining terms and conditions and things. Otherwise, we're just going to be left in the dark with, um, quantifiability, which isn't bringing us to resolvable, ultimate, absolute answers.
Yeah, I don't think that science has the type of answers here on these things that you would like to have, that I think that scientists maybe of old would have expected that we would reach at some point. Um, the history of the study of electromagnetism has been mapping the surface level observations of it, and no one has settled on kind of like a
And
deeper answer for what the magnetic field is. We can say there's a thing we're calling the magnetic field, and we can say what it does, but what is it? Yeah, I don't think that there's an answer to that.
I mean, I think there is an answer. I think the mainstream is kind of just really put it back up on the dusty shelf and not really cared. But there are answers. Like when you look into some of these ether field theorists, you know, they've actually given a definement on magnetism, the magnetic field, magnets, and what these things are and what they are not. And what they are not is they are not virtual photons or virtual particles. All
I
right,
don't
and
think that
that's
that's.
kind of
I actually think that that's literally an inaccurate explanation of the theory. Like, as far as saying that they are virtual particles, it's a different matter. Look, I'm not against ether at all. I think that ether is a very valuable framework. I'm interested in what the ancients had to say about it. I'm not in any way opposed to asking the question of, does that provide the deeper sort of conceptual explanation of what these fields are? So I don't think we have any disagreement there.
well, from the ether field theorist perspective, there's only one field ultimately, and
Mhm.
it's only current science that perceives fields to be, separated and ununified.
Yeah, like
Like
the
you'll
different
have
legs of the elephant. Yeah.
right, but ultimately, all these fields are united, right? So that's what they've done. They've been able to unify all these different fields, which is what the mainstream claims to be pursuing. However, they're working quite the opposite direction.
Yeah, I mean, everyone likes the idea of some sort of grand unification and is pursuing it under different frameworks, and is probably pursuing it wrongly for the most part, because that's what happens. Like when lots of people are exploring things, most are going to go off in the wrong direction. And I find a lot of value in going back and rereading um, like what people used to say about the ether, to give me a different framework for thinking about the fields and what they could be compared to the mainstream.
Well, yeah, I mean I mean if you're going to be honest in the conversation or just in science and with yourself in general, right? You kind of want to remove the hubristic notions, right? Um, when you're never looking for the answers to the answers you think you already have, like you could just be building on top of something completely wrong with zero foundational, support. And that's kind of where we're at today. Like a lot of these scientists are just building off of things that were wrong from the very foundations.
You know,
And
I agree. I think that the virtual particle explanation is actually really bad on a lot of fronts. Um, and yeah, and I'm very interested in like re-exploring. Look, so I mentioned this before, but just because it was something that was very cool that I went to a couple weeks ago. But I went to a conference of physicists, mostly academic physicists, though some people from other fields. Very small conference, and the conference presents itself as kind of a refuge for anyone who's sick of like the dominant mainstream physics conventions. And the talks were all over the place. And one of the talks was on reinterpreting the vacuum of space as being filled with a dielectric medium, and understanding light as a wave, not in something purely mathematically abstract, but in something with much more literal physicality, as in the vibrations of this dielectric medium, and actually attempting to calculate what the speed of light is, based on specific observations of things like electrons and muons and stuff like that under this model of thinking of the vacuum of space within this way. And the speaker made it very clear that within this framework, the discussion of virtual particles is basically viewed as a misinterpretation of the stretching and compressing of the dielectric medium. And like, I thought that was really exciting and very fascinating. And these ideas may not be super widespread or popular within physics, but there are some people who are looking into them.
Yeah, I got to get back to work, but yeah, I mean, yeah, hopefully more people can step up to the plate and actually try to perceive things, separate from what we've been indoctrinated with.
Sure. Yeah.
But yeah,
Happy to share.
So Mateo.
Just making up a whole bunch of stuff there's no physical evidence for, but then think it's totally okay when he does it to just be like, yeah, there's 10 other dimensions, but you can't see it because our reality is frozen by a standing wave pattern to a 4-dimensional subspace within it. It's just like it gets really convoluted in exactly the same, like they're making up stuff in hidden dimensions way that string theory does, that he rightfully complains about as well.
It's actually counter space. Are you familiar with Ken Wheeler?
Ken Wheeler? No.
Oh man.
Let me look at
I gotta send you. I gotta send you a playlist or something. So you're gonna be able to engage on a much deeper level with a lot of people in this room if you watch. I'll make a playlist for you on Ken Wheeler. You know his term, his dimensional term is counter space. And you know what? I'm not angry about it. And it does have a funny name that people meme on. You might see that like, oh, counter space. Yeah, my kitchen has a lot of counter space, right? But that's obviously not what he means. But everyone likes to use their terms, in that sort of snake oil salesman. Who knows? Maybe they're right. Maybe they're right. But
so many terms. He makes up so
but
many terms never used so
but yeah,
quickly.
you got your ears got to prick up when you hear someone using a self-coined term.
So many of them. It's like this is whole paper. Every page is like 10 new self-coined terms and symbols. It's so unnecessary.
Yeah, but does your model even have the Lagrangian points figured out? Jeez.
What I'm working on has a Lagrangian, I'll say that.
What's your take on whether there is or isn't a universal frame?
Okay, so it's a couple different ways for me to
no pressure at all, man. If you say something, trust me that I don't know who's gonna chime in, but trust me that if you say something that implies something, I'm not gonna be like, I gotcha, like maybe some other people would. Just speak from the heart.
Yeah. When we talk about frames, we're talking about coordinate systems, grids.
Exactly. A universal coordinate system. Right. Is there a center? Is there a 0, 0, 0 location? Or is it, as the relativists tell us, it's like, nah, there's no center, there's no boundaries, it's infinite, it's nothing, that's moving. What does it matter? Both are correct, both are wrong. Who cares?
Well, yeah, so the first thing I would say is that strictly at the level of the coordinate system, it is something we're making up. Like, no matter what the nature of the universe is, you could choose to draw the coordinate system any way you wanted. So the question really becomes, is there a natural choice? Are there some choices for it that make more sense because motion of objects looks simpler and cleaner on them than it would work on
that's
others?
That's not what the universal wanted. In the universal reference trying to be like, no, it's all still, and there's a spot in space, and that spot will always remain that exact coordinate. And basically as simple as that. Like a very firm, strict, stationary, 3-dimensional matrix coordinate system. Is that something you don't believe in?
Well, I guess what I'm trying to say here is that the coordinate system doesn't inherently have any kind of physical meaning to me at the outset. Like, we need to be able to say more specifically, like, what depends on it, right? So, like, okay, so let's even take the flat Earth model here of you can imagine
Location.
you can
Location and speed is what would depend on it.
right. Well, no, exactly
How
right. Yeah,
fast
yeah.
is something actually traveling in the pure universal complete sense compared to the one true ultimate stationary coordinate system? Now, if you don't believe in that, just let's just not beat around the bush and just say I don't believe in a one true universal stationary unmoving coordinate set. Just get it off. Just get it off your chest if that's what you believe. I'm not going to insult you.
Well, so let me ask a clarifying question here. So let's imagine the flat Earth. Let's imagine a flat plane, and the flat Earth
Can,
is stationary
you're
within it.
going on a long thing, man. Yeah, this is. I'm not
Dude,
trying
he's
to be rude,
explaining it, man.
but it's a yes or no. I do or do not believe in a strict, stationary, unmoving, 3-dimensional coordinate set that truly exists.
Right. So
A
what I'm trying to say
space,
is
a
that
spot in space is a spot in space. Period.
right. So what I'm trying
If
to
you want
say
to
is,
say no, it's not as simple as that, then just say no, it's not as simple as that, in my opinion.
well, it could be. So
Okay, it could be. Okay.
the first thing I want to say is that inherently, I think the idea of the coordinate system is just something in our head. Like, I don't in any way understand why one spot in space sort of, I don't know, inherently has some sort of position name compared to another. So the kind of the next question would be, if you imagine the world, and I said feel free to use the flat Earth here, that is stationary in some coordinate grid versus one that's moving within that coordinate grid, what's actually the physical implication of that? Like, what is actually the physical effect that we are testing for that will appear if it's moving with respect to the coordinate grid versus not? Because kind of what I'm trying to get at
Rotation
here is
plays a big
why
role, in my opinion.
but I just mean that, like, the coordinate grid isn't something that literally exists. Like, we're not actually looking around and seeing a big grid with like tags at every single point. If that was there, if it was something that wasn't in our heads, then yeah, I'd be like, oh, we're moving with respect to it. Like, but like, if it's kind of something we're making up in the first place, and but we do
I
want to
think
see if there's
rotation.
one
I think
right,
rotation kind of proves it, though, at least to some degree.
right, you know,
Rotating
yes.
in relation to what?
Well,
If
but
if I if I spin around in a circle at night, right? You got all the stars in the sky, and I spin around, like a little kid. As a kid, you ever like stretch your arms out and spin around till you're dizzy, or maybe you look down at your toes. You spin as fast as you can, right? I find it ridiculous for anyone to say, you see the stars in the sky or the buildings around you. You're spinning around in a field, and you see the trees in your vision spinning around you. It's like no one's gonna tell me that I'm stationary and the trees are circling me. It's like no, I'm the one spinning, and
it could
and
be
as
just
and as soon as
you.
as soon as you take that to observing visually something more than like 50 miles away, then if you spin as fast as you can with your eyes open, looking at things in the distance, as soon as anything is over 50 miles away from you, they would have to be breaking the speed of light in order for you to be the stationary one and them to be actually circling around you.
Maybe you can break the speed of light. Maybe the
Oh
universe
shit.
is
Okay,
This is
you're not the average glober. Okay. You're the
yeah, I
first
don't know.
glober on here to ever say you can
also.
break the speed of light. Shit, I'm not prepared
I
for
said
you.
maybe. I said maybe.
I have to interject here and say that relativity is not the same as point A versus point B in motion, because now you're taking into consideration the relativity between all your atoms, all your particles that are made up of you, spinning to maintain a centrifugal force. So when you say relative to what, you're going to have to talk about one unit rotating.
So,
either I'm spinning or they're orbiting me. Those are the two black and white scenarios you could describe the appearance of what's going
You're not
on.
one thing.
And one of them fits within everything I've ever been taught about the rules of nature and
You're not
physics.
one thing, dude. You're being
And
held
then one
together.
of them, and then if I'm actually stationary, it's actually, I thought I was spinning, but I'm actually counter rotating, and I'm the one actually stationary, and the world is spinning around me. Then anything past 50 miles away from me that I can see with my own two eyes is gonna be ordering me faster than the speed of light. At which, but this guy said, "Hey, things can break the speed of light." So
I didn't
I'm not
say
prepared for
I
that.
thought they could. I'm just saying I don't know, maybe. But I think the important thing with the spinning one, there's something much more important to the spinning example than the fact that the world looks like it's rushing around you. It's that you know that you're spinning even with your eyes closed. You don't need reference to
Tell that
outside.
to the man on the train, right? He doesn't know he's moving.
Well, that's a good distinction, right? You do feel the spin, but you don't feel the steady train ride.
Yeah, but if you're in the center, okay. I'll have to get back to you on that one. You can feel the spin.
You're not
Well,
one thing, Fundy.
Nah, I think you do feel the
there's
steady train
momentum though.
ride. It's all depending. Oh, all right.
Yeah, your arms fly out.
Hmm. You need something always pulling inward so that you don't fall apart into pieces going outwards.
Right. And also,
There's a constant acceleration.
has anyone done the figure skater thing, or just do like the little spinny chair thing where you start with your arms out, bring your arms in, and you speed up, and you feel like the force that takes. Like if you're spinning, it takes more effort to pull your arms in than it does if you're not spinning. So even in the absence
That proves it.
any understanding of your relationship with respect to other objects, there's an intrinsic detection of spin. There's a strain within your body while you're spinning that isn't while you're not.
Do you know what happens to weight when you spin something up like that?
Yeah, you feel heavier. It's like a centrifuge.
No, opposite. Opposite. If you were
He's roboting for me.
Yeah, Dieslow, you're roboting really hard, man.
That's too bad. I think he had something very interesting to say. Give it a shot as soon as you can, Dieslow.
Yeah, I wanted to know what he was going to say.
Still roboting, unfortunately.
You're lagging hard, Die. Yeah.
So the fact that you can spin in a circle and reason pretty logically, just not scientifically, but just like, come on, and be like, all right, everything around me is spinning, therefore I must be the one spinning, and things aren't breaking the speed of light. The thing is, you can have another observer 5 feet away from you who's spinning the opposite direction and say like, oh, that guy thinks that everything around him, everything 50 miles away from him is going the speed of light in the opposite rotation. Now, obviously, that just breaks everything. Yep. Yeah, go ahead, Dieslow.
Well, maybe you can fill them in, Fundy, because I'm kind of going through a canyon and I might break up again. But I don't know if you ever saw the video that Ken Wheeler did, and I think Veritasium did a similar video where you take a 20-pound weight with a 4-foot pole, right? And most people couldn't lift that 20-pound weight off that 4-foot pole holding the end of the pole, right? Because you're not He-Man. Yeah. However, if you spun that weight up, right? If you spun that weight up at the end of the pole, all of a sudden it seems as if the weight just vanishes and you can now lift this thing above your head.
Yes.
With quite ease.
I'm not sure I believe that is as miraculous as some other people might. I believe that you are lifting the total weight of the bar. So if there's a 20-pound weight attached to a 10-pound bar, so a net 30 pounds of weight, when you spin it up like a gyro, right, it does become way easier to lift, but it doesn't become weightless. It becomes a 30-pound weight with its leverage displaced in a very interesting gyroscopic way.
I would say I would say this is proof that weight isn't a force, rather a force is required to counterweight. And if you understand all the variables, I think there's 6 or 7 variables associated with weight, then you'll quickly
I
realize
do.
that, right, then you'll quickly realize that weight isn't a thing of itself, and it certainly isn't a force.
Well,
In
it has the same
I
weight, the wheel, right? It's just the fact that when you turn it, the movement processes, and so the energy that it's always moving with is the one that you use to spin it up. So the precession of the angular momentum causes a vector to point in a different direction of what it otherwise would have been, and that would be upwards. It's going to stop
They
once
can
the
only
wheel
lift it
stops
in one
spinning.
direction. If they like lift it up and over in one rotational direction, they wouldn't be able to do it the other way.
Yeah, I mean, yeah, I'm really sorry, Dieslow, but um, if there's like a long pole that's only 30 pounds, if it's in my opinion, it's all about torque. And I can't really explain. I could try, but I'm not going to because it'd be a messy explanation. But holding a 30-pound bar by the very tip of it puts so much torque on your wrist. Even though if you grab that same 5-foot long 30-pound bar by the center of it, anyone can, most grown men can easily lift 30 pounds, if they're holding the center of the pole, but not many men could lift 30 pounds holding the end of a 5-foot pole. And the miracle that happens, the gyroscopic miracle that occurs when putting a 20-pound spinning weight on the end of a 10-pound bar is that through some gyroscopic physics, the weight becomes distributed where it doesn't matter where you lift it from. The weight is somehow distributed in a way
It's
torque
called
wise evenly throughout the pole, so that no matter what part you're lifting it from, it only feels like 30 pounds. But it doesn't feel
it's
weightless. It just feels like it's total net weight with no leverage involved.
it's called gyromagnetic precession, which is more accurately field friction, and it is torque. It's generated. It's essentially torque. Yeah, magnetic torque, field torque. I mean, obviously you
I
have the
don't.
physical rotation taking place, right? But if you look at any gyroscope, it'll eventually flip itself over due to this gyromagnetic precession.
If floating in a vacuum, in a weightless vacuum,
No,
sure.
no, you can do this in a non-vacuum environment. Now, if you did it in a vacuum environment, yeah, you're going to get what's known as the T handle effect. You can see that on the ISS station, where you take a T handle, you spin it up, and you let it go. It'll literally flip back and forth. If you've never seen that, there's a video you can find on YouTube. Type in T handle ISS station, and you can see that phenomena.
That sounds like it's in a weightless environment, but that's fine. Um, so are you telling me that in so not on Earth, do you not want to make any of the examples on Earth? You want to put them in
Yeah,
a
you can do an
falling?
example. If you've ever gone to like I don't know, restaurants when I was a kid used to have them, but it's essentially you put a quarter in this thing, and the quarter rolls down this
Yeah,
little alley, right?
yeah, I'm
And
familiar.
right, and it appears as if the quarter keeps itself upright and speeds up as it processes down this little alley.
Yeah,
Um, right, it's a similar concept.
right. But gyromagnetic precession, in my opinion, um, that would be like in a weightless in a weightless environment. You could have like a magnetic point, and then you could spin like a, I don't know, like a metal Beyblade, if you're familiar with a spinning
Yeah,
metal top,
the
right?
Beyblades, dude. My
And
kids love
that
those.
there's gonna be like instability, or maybe magnetic instability, or guide paths or something, that it's gonna be on one side, and then it's gonna wobble more and more and more, and then it's gonna flip upside down and then reduce and wobble until it finds a balance point. and then it's going to start wobbling more and more again until it destabilizes and basically restabilizes on the opposite pole. And
Well,
I get that.
this is like the same. This is
Power.
the
Isn't
same
this just energy?
phenomenon.
That has nothing to do with the way
If
people
the
can
Glovers,
pick up
can you guys hear me?
a spinning weight attached to a bar. When you spin the weight on the end
Can
of
you hear me at all?
in
Or
my opinion, it's not really related.
I don't know. Can anybody hear me?
Yes, we can hear you.
Oh, he was just chanting through me. Oh, okay, I got it.
Yeah, we could hear you the whole time. Sorry, I couldn't get to my phone. Yeah, he was
That's cool.
chanting to you.
All right, I'll
He was
just back.
chanting to you.
I'm just gonna back out then.
No, you should keep going.
Yeah,
But
There's
the
nothing
point with the
there's
spinning
nothing
coin.
there's
Hold
no
on, Fundy.
magnetic
I mean,
factor
you're
going
going really
on
hard,
the
Fundy.
spinning
Like,
weight lift.
So I might need
Yeah,
to get
he's
going in
on
a
his.
second. I did have a thought to finish on the whole objective frame thing. So, I was saying there is like the coordinate system itself is something we've made up. Like, we could just choose to draw a grid in any shape or fashion. It just definitely might be more logical or reasonable to do it some ways over other ways. Like there's no law of physics that says we have to use a sensible coordinate system. Like I don't know, like we could, instead of having nice latitude and longitude lines, have like painted crazy lines across the earth, just had someone drunkenly run around and be like, this line's 2, and then another one that's squiggling all over the place and be like, all right, this is 3. It's just like a marking. But right, but I do think that physics is telling us that there are some ways of drawing it out that make more sense than others, that are more natural than others. So if there's an absolute reference frame, what I would like to know is like, what concretely is the thing that happens to you when you are in motion with respect to that absolute reference frame. So like, maybe the absolute reference frame is defined by an ether fluid, and like that is what we're saying is like, okay, we could have drawn out the coordinate system any way we wanted. We could drunkenly slide the coordinate system around in our math, but obviously we should pin it to the ether fluid as the fundamental thing, and then we can say what it means to be in motion is to be moving through this fluid. So I'm just using that as an example of like,
It's what happens every day for everything you've ever been a part of or witnessed or seen. It's how we all live our lives in every aspect of our lives, unless you're launching satellites and dealing with GPS or something in a belief system of ball physics. But yeah,
well,
that's how
didn't this
everything
whole argument
works.
start with somebody just wanting, like, if I move around on Earth, is there some way for every observer in the universe to see that I moved that way? I don't think we're going as deep as to the math or underlying physical principles. I think somebody just wanted to know that, right? So you can compare against the cosmic microwave background. Now, if there's something relative to that outside of it, that's a different issue. But everything within the universe, that's how we track the years. They ask in relativity, why do we say 13.8 billion years? We use the background as a relativity anchor.
yeah, under certain theories, you get out that the cosmic radiation would be 13 billion years, dependent on some of the specific assumptions of those theories.
Well, the year isn't important here. It's the reference point of everything within the universe.
Or the day, year, those are good anchors. But zzpop, man, if you're asking what would it be like, man, like what would it really be like if there was a universal reference frame? It would be exactly how we experience life as individuals. It'd be just like that. It'd be very comprehensible, relatable. It'd be exactly how everyone takes everything for granted in the first place.
Well, what we
I'm
take
gonna
for
see. I'm gonna see
granted
if I can send you that
is our brains
real quick,
lock onto
CZ.
the ground. Like, what we take for granted is our brains lock onto the ground. Like, our
Doesn't make it
relationship
wrong.
our relationship to the ground is what it is. What I'm asking is, what would actually be the feelable difference between saying that the ground is stationary versus that the ground is moving?
If you're asking me, what if we are really all on a constant speed, constant velocity moving train? I'd say, fuck. I guess the flat Earth could be on a constantly
Put the
moving
flat
train
Earth
at
on
the
a
same
train,
speed.
on a steady train. What are we expecting to feel differently? If the that's why I said
We're
use the
expecting it
flat.
to feel just as it is.
Yeah,
It's not proof, but our life, every example of everything anyone's ever done, aside from NASA, tells you you're stationary, and that's how things work. And it works out perfectly in math on any personal level if you're not launching satellites. Everything works this way for all of us, unless you're a part of NASA. Theoretically, I guess, hypothetically.
well, you're stationary to the Earth because it's the big thing here, right? So then, if we want to say is the Earth stationary or not, well,
It
stationary or
feels
not to what?
everything operates that way.
Well, but sure, it feels that way, right?
Everything operates as if that is the case. For anyone to disagree, it's like,
Nobody
all right,
disagrees.
can convince me I'm not convince me the ground isn't relatively stationary. Not don't take that word the wrong way. I mean, like, there's seismographs, there's little vibrations or whatever, but convince me the ground isn't pretty much basically still.
I'm not saying you can't view it as still at all.
Everyone does.
Sure. I'm just saying, like, if you want to say that that's more of just like a bias of the human brain, then we actually have to say, like, concretely, like, what would be physically happening differently if it was in motion?
Right. Maybe we're moving at 1,000,000 miles per hour around a galactic center, around a sun, and spinning so slow to detect. And it's like, all right, I'm ready. I was told that, but you know what? I'm going to go back to my roots because that's what every single experiment ever actually demonstrates. And now I need to wonder, why did I ever believe these folk tales that I'm moving at a few 100 million miles per hour right now? Because everything ever that any of us have ever experienced tells us the ground is a pretty good reference to stillness.
Sure. I mean, that's the brain. That's our intuition. That's our feeling.
That's everything except for fairy tales, in my opinion. Convince me otherwise. It's
I,
really every evidence.
I just okay. You're looking at the ground right now. You feel like it's stationary, right? I'm just asking.
Einstein said it himself.
Right. Imagine, and I'm not even saying you can't look at it that way. I'm not saying that's not valid. I'm not saying that's not a valid way to think about things. I'm just saying now imagine the Earth is hurtling through space at this immense speed. What do you expect the difference of feeling would be? Like, what would tip you
Well,
off that that's happening?
if the Earth were spinning, see, this is where we bring up the Goldilocks miracle zones of the globe Earth, right? If the Earth was spinning twice as fast, oh boy, would it be noticeable. You would have to angle skyscrapers at a 45-degree angle at 45 degrees longitude to counteract the centrifugal force. But oh
Yeah,
no, we're in a Goldilocks zone of spin where the centrifugal force and the downward gravity towards the center just so have to be unnoticeably partnering up with each other. So again, it comes down to a nice story and very convenient tactic in your storytelling. And the world, the nihilistic universe that it was taught to us as children in school, just so happens to cover its tracks because there's no reason it shouldn't be spinning twice as fast. Who determined the speed of rotation? Oh, it's nothing determined. It just happens
You don't
on
understand.
top of the rest of the 100 miracles.
It's Goldilocks to you because you evolved in it. That's why.
wait,
Yeah, yeah.
I
But you understand that if the Earth was spinning just even a little bit faster, we would have to tilt against the surface, not perpendicular. We wouldn't have perpendicular skyscrapers. We have tilted skyscrapers. If the Earth was spinning even just a little bit faster, so lucky us that it's a
And
Goldilocks
no
zone.
air, and no air would be moving along this Earth either.
Wait, I think we got a little off topic here because we agreed earlier. Spin is definitely real. Spin is feelable. You close your eyes, you feel spin. So if the Earth is spinning, that's got to appear as that's got to be a feelable centrifugal force, as they call it. To your point there, but before that, we were talking about not the spin of the Earth, but the sailing of the Earth through the universe. So I like these photos that someone's posting right now of the turtle with the flat Earth on it. I think that's actually perfect for the visualization.
We're not going in straight lines, though.
Right.
In the globe model, everything is orbits and circles, and so it has to be slow and a big enough circumference or a big enough radius and a slow enough rotation. And thank goodness in the nihilistic, unintentionally designed, not that I'm a Bible guide, but any glober has to admit, thank goodness the orbit and the rotational speeds are slow enough and subtle enough that it comes across as a flat Earth to your senses. Thank goodness.
Yeah.
It comes, even though everything is circles and spinning, the spin is slow enough and the circles are large enough that everything feels stationary and flat. It's like, all right, well, maybe think about that.
Yeah.
Lucky, like I said, Goldilocks.
Oh, the air's also breathable. I mean, like, I wouldn't even be here.
That's why, yeah. That's why I said now take those two things in cooperation with the other maybe 100 off the top of my head miracles of this place, and that should allow you to realize I'm not making the fallacy of like the sentient pool of water waking up in a pothole says, man, this pothole must have been designed for me because my body of water perfectly fits in it. It's like, obviously, if it overflowed, then it wouldn't be that body of water. It would drain, outside of it. But that's not what the case is when a million miracles are stacked on top of each other. That's when you realize, there's enough here to say that this can't be happenstance.
You're talking a lot, but can you shortly summarize the reason for the tilt on the skyscrapers again, please? Can you do it shortly? I just want to understand it.
Yeah, so basically vectors.
For a bit, but thanks. Love to pick up again sometime. Peace.
Good,
Peace, man. Nice talking to you. So the thing about tilted skyscrapers, right? You know that if you're on a mirror, I'm going to rely on you to piece this together. I'm going to give you everything you need in order to piece together. All right. So
go on, please.
Yeah. I'm just telling you, it's going to be an analogy. So here I go. If you're standing on like a 50-foot radius merry-go-round, right? If it's spinning very slowly, you can just stand straight up. You don't need to like brace yourself. You don't need to spread your stance of your foot position, right? If it's spinning like once every 24 hours and it's just 50-foot radius, right? You can stand on the edge, no problem. You can just stand up perfectly still, right? You're not gonna fall off and get flung off. It's spinning very slowly. You can stand straight up and not get flung off.
The further out you are, the faster your speed is.
Right. That's why I said if it's spinning very slowly, you can stand perfectly straight up on just a 2D circle merry-go-round, right?
I understand.
Flat floor spinning. Okay. Now, if the floor is flat and it gets a little faster and how fast it spins, right? You can no longer stand perfectly straight up. The way that you stay standing on a faster spinning merry-go-round, flat 2D circle spinning floor, right? Is that you actually have to lean in towards the center with your head, like a Michael Jackson routine, right? You actually have to stand firmly planted. Hopefully your feet don't slip. Let's imply there's enough friction on your shoes.
What you're getting at. Yeah.
So there's two vectors going on. There's a centrifugal vector and there's a downward gravitational vector. This applies to everything other than 0 degrees latitude on a globe. The same thing applies. So just like you would have to lean like Michael Jackson's performing Smooth Criminal on a merry-go-round if it was swinging fast in order to keep your feet planted firmly without being flung off, you have to lean your head towards the center. On a globe, depending on what latitude you are, if the Earth were spinning just even a little bit faster, tall buildings would need to be angled in order to balance out the gravitational vector with the centrifugal force vector.
So why not at the speed it's doing right now then?
Because we are in a Goldilocks zone where it's so subtle, it doesn't matter. We can just pretend like the Earth is stationary.
Way faster, it would be the same effect. So now you've explained that for a very long time. Now you imagine a spinning wheel again. Imagine a spinning wheel, and you tie a string on a handle at the very edge of this wheel, and then you spin it up to a speed. Are the strings going to bend or be completely straight?
I'm not sure.
They're going to be completely straight.
If you're telling me this is like a
the point is that if you make a tall skyscraper, the further up you go on the skyscraper, it is going to be traveling faster than the bottom. So it will be able to get straight just like it is on Earth. And the reason is you build a foundation, then you put slabs on top. The further up you go, the faster naturally it increases due to friction, and the speed is greater up there relatively to the ground.
Oh no,
there's no problem keeping a string. Otherwise, a string. I'm going to finish up with this. Otherwise, a string would twirl if it's spinning on a wheel as well, but it doesn't, no matter how long it is. It will,
listen, I don't think you want to down this hill. All right,
acceleration is different. If you keep accelerating, that would be hard.
Hold on. Imagine you have a furry ball. All right. Imagine you have a furry ball. Okay. So there's hair follicles. So there's hair follicles or whatever, fur follicles, whatever, basically covering every square inch of a ball. Then you rotate it quickly. Then you rotate this. It's fur sprouting out of it in every direction. Then you rotate this ball pretty quickly. You know that the ones on the equator of the spin are going to be the only hairs basically being straight and not bent at the root. And the closer you get to the north or south pole of that ball, the spinning ball in one direction, the hairs at the north pole of that ball or the north axis of that ball, they are going to be bent 90 degrees because the ball they're attached to is spinning.
Well, if they've made this ball with every hole pointing outwards in one direction, and if it follows a sphere, then no, that wouldn't be the case, right? Unless you're spinning it in one direction, which you are. So you are bending it with your own acceleration in one direction. Obviously, those things are going to bend.
What? Yes, obviously.
Yeah. That's because while you're accelerating it, they will not keep moving set at a constant speed.
I don't know what to do with you, man.
Everybody, if you're spinning at a constant speed, there's an equilibrium vector at every point on that sphere, pointing outwards in one direction. So it doesn't matter.
All right, you win, man. I give up. You won this one, guys. He's got it.
Sarcasm doesn't help.
Not you. You made a good point. I give up. I take back what I said.
I still love you, though.
Love you too, bud. That's hard for me to say when someone dominated me that hard just now, but
well, I don't know. Yeah. You can come to my swing set.